Hello. So let's get started with this very fun class. And here we are. Okay, slideshow from the beginning. Okay. Contact information is there for asking questions or anything else that might seem relevant. Now, why is this subject so exciting? Well, it's psychologists say one of the reasons why humans have pets is because we yearn for another sentient creature on this planet, other members of a different species to talk to share, to so forth. And when we think about life on other planets, this Mr. Spock, from Star Trek is what we're thinking about. And the point that we're making here is that the expected huge plethora of alien life out there is probably, a lot of it is one-celled or simple plants, or they not necessarily millions of species of sentience. Okay, so when we're thinking about life, this is what I'd like you to think about. Okay, a simple bacteria, because this is probably what we're going to find. Now, what is life? You can't find it if you don't know what you're looking for. So when we're looking for life, what is it that we're looking for? We're not saying that life has to wake up and say hello in perfect English. So what is that minimum threshold that separates biology from chemistry? Okay, when does chemistry give way to biology? Life has to fulfill two criteria. There has to be metabolism, and there needs to be reproduction. So metabolism is ingesting something. You breathe it in, you envelop it, you eat it, you absorb it through your skin, whatever. You ingest something, and there are chemical processes. I'm not going to start throwing terminology around. Okay. Some chemistry happens, right? This is the input. Chemistry happens, and there's an output. You're all familiar with, you bring in oxygen, and the oxygen helps your individual cells to metabolize the bagels and lox or whatever it is you just had for pasta for lunch or dinner. And so oxygen in, food in, chemistry, and the output part of it is carbon dioxide, okay, which you then breathe out. That is metabolism. Any kind of input, chemical change, and then output, which delivers energy to that living, possibly living thing, okay, cell, we're going to call it. That is metabolism. Now, reproduction doesn't mean me producing a baby. What we're talking about here is cell reproduction, which, again, drilling down, means you've heard of DNA. Okay. A simpler molecule that our body also uses, and that the earliest life forms would have used, is RNA. It's not a double strand, it's a single strand. Okay. Now, biology is going to rely on what's possible chemically. So in order for there to be metabolism, there needs to be something to ingest, and there needs to be a power source, right? There's heat, or there's the sun, when the sun's working on plants, they'll be then producing sugars and oxygen and so forth. Okay, so you're going to have inputs that include power, some kind of power source, photosynthesis or chemical energy or heat, right? There's this something. And then you're going to have an output. That's metabolism. Reproduction is this RNA molecule has a way of making a second RNA molecule, and then four, right? Each one is going to reproduce, and then you'll have four and so forth. Okay. That's that's necessary. Otherwise, life is composed of one RNA strand, which isn't going to last 4 billion years. Okay. All right. So how likely is it that life is going to emerge on other planets? So one of the reasons why the story changed in the last 20 years, and we're now saying life is just an emergent property of the right physical conditions, physics, that's Rick, and chemistry, right? Now, why do we say that, right? Because of what happened on Earth. And this is a picture of a lava field, right? Now, one of the things that we have to keep in mind is that life emerged on the Earth very, very quickly. The Earth, existed was a planet at 4.4 billion years ago. We had a solid surface, lava, but mostly solid surface. It wasn't liquid or gaseous or anything else. Okay. It wasn't all lava. There was some crust there. Okay. At 3.9 billion years ago, there are signs of life. There's proof of life indisputable, mostly indisputable, in the fossil record. Now, there was undoubtedly life way prior to that, because a little strand of RNA that qualifies as life is not going to, it's not going to show up in the fossil record. You need at least a cell wall. Okay. And please remember that, excuse me, a half a billion years, just half a billion years after we had a solid crust, we've got proof of life. That is, 500 million years sounds like a long time to a human being. But in the cosmic sense, this is practically nothing. It took a lot longer to go from the first forms of life to a significant amount of free oxygen. It was 1.5 billion years. Right now, life changed immensely when there was a huge amount of oxygen. Something to know about oxygen: it is extremely reactive. That's why iron rusts. Okay, and metals deteriorate because of the chemical action of oxygen. And oxygen is also what feeds fires. If we had significantly more oxygen in our atmosphere, we would have worldwide forest fires. Nothing would grow, taller than this. And it's oxygen is very, very reactive, right? The fact that we breathe it, we forget. how it's not everybody's favorite element or gas. Right now, the first forms of life we know were bacteria. Well, the first, I'm going to say complex, something with a cell wall around it, were bacteria. And they were living in a relatively almost completely oxygen-free environment. And some of those bacteria started releasing oxygen as a byproduct, right? As a what they were giving out, right? So they were taking in other things and pumping out oxygen. Unfortunately, oxygen was also poisoning them. So the first runaway destroying your environment was these bacteria who produced oxygen and killed everybody that couldn't live in oxygen. So there's a technical term there that I just threw out that I wanna talk about right now. So we started out with the idea of a single RNA strand, and I just said a bacterium has a cell wall. It's really important in the development of this transition to life that these bare molecules were able to develop a protection, because what happens with metabolism and with reproduction is you want to accumulate things inside this cell that allow efficient metabolism. If you remember way back, the mists of time, basic biology, what happens inside of a cell, endoplasmic reticulum and mitochondria and all that, right? Messenger RNA and so forth. All of those things, the reason that they work is because they're working inside of a protective envelope. They're not being swooshed around by water currents. And it's very important that you have a cell wall that is made of lipid fat, basically. Okay, because as you know, fat won't dissolve and disappear into water. Water can't get through a fat barrier, a lipid barrier. So having a cell wall that that is lipid based means that you don't have to worry about the water inside the cell and the water outside the cell trying to equalize themselves. You can accumulate a greater density of these interesting molecules, right? Keep them inside the cell so that you can have efficient metabolism. Now, I want you to just keep that in the back of your mind, that idea of how the cell is constructed. So we're starting with the DNA, and then we're going to find ways to be more efficient with metabolism, and we're going to put it inside of a cell wall, right? We started seeing bacteria at 3.9 billion years ago. All right, now, one of the fun things, because I have a mischievous sense of humor, and so does Rick, is the finding of exoplanets through various means, which we'll get to, means that what we used to do when we were all kids, which in my case is, back in the Pleistocene, what we used to think is, okay, we have a mechanism, we have a proposed mechanism, spinning planetary disk, for how our solar system came into being. So heavy elements, the rocky grains, dust grains, just through physics would have accumulated closer to into the gravity well caused by the sun, right? And further out, the lighter elements, hydrogen and helium. So we've got the Jupiter, Saturn, and then the ice giants, Uranus and Neptune. And we have the Kuiper belt, which is composed of bodies, small icy bodies. Excuse me, some comets come from the Kuiper belt. And there's another belt way further out called the Oort cloud, which is where the longer period comets come from. And that's all just icy balls. Okay. And one of the things that we've learned about our own solar system is that one of the very cool objects from and that's not a temperature designation. Okay, cool, yeah. The Kuiper belt objects, KBOs, all right. One of the coolest of the cool is something that back when we didn't know any better, we thought was a planet. And it absolutely is not. This Pluto, Makemake, Eris, and a couple of other things are very interesting Kuiper belt objects, but none of them have the size, the mass, the orbit of a major planet. Okay. And so when Pluto was discovered, we thought, state of the art 100 years ago, we thought it was a lot bigger. We thought it was Neptune sized, and then we thought it was, Earth size, and then we thought it was Mars size. It turns out it's 1/5 the mass of our moon and less than a half of the diameter. It is really, really small. It's so small that it could, physics-wise, it could revolve around our moon without disturbing our moon's orbit around the Earth. It has so little mass. It's really, really tiny. And if we had known how tiny it was, no sane person would have said, oh, this is a new planet. Because the moons of Jupiter are so many times bigger. The moons of Jupiter, our moon, our little moon in the sky, is so much bigger than Pluto. It's laughable. So, but 100 years ago, nobody knew that. Okay, we know that now. So it's time to, you get new data, you change your mind. Okay. So that's what the American Astronomical Association did, or the International Astronomical Union did. All right. So what we thought was that every single planetary system out there is going to be like ours because it makes sense. Right? We came up with this theory and logically everything fits. Why would a solar system not evolve in this incredibly logical way? Well, we started looking and finding and getting accurate information, which we didn't have about Pluto, accurate information about these other planetary systems. And lo and behold, practically none of them look like ours. The closest to ours is the TRAPPIST-1 system. everything else is incredibly different. You know, big Jupiter-sized things close to the sun, and things that are that have only Jupiter-sized objects, or only Neptune-sized objects, or things that are in weird places when you look at our solar system. So it's been a wild ride, and it has also been an object lesson in humility. Psychologists and spiritual leaders say, assume you don't know what's going on and ask a lot of questions. Don't jump to conclusions. Don't judge situations. Don't judge people. Well, as it turns out, we were a bit arrogant, assuming that we knew everything there was to know about planetary systems based on one example, right? One example proves absolutely nothing in science. Even when one example is all you've got, we should have been more humble. Ah, humanity. Okay. So one principle here is that biology depends on chemistry, but chemistry depends on physics. If your planet is right near a hot star, the surface is going to be molten. It's going to be hard for life to develop there. Any life that we might even remotely recognize as such. So what we do when we're trying to assess, should we spend resources looking for life on this planet, right? We look at, what does the orbit look like? Well, first off is what is the star? Because if it's a very young, hot star, the planetary disk is probably not even finished forming planets yet. And the problem with hot, bright stars is that they burn up their hydrogen fuel very quickly. And, I was saying that, oh gosh, life just emerges so quickly. But remember, I'm talking about 500 million years. If the entire life of this hot, bright star is only about 25 million M, not B, years, it's not going to shine long enough for life to emerge, intelligent life to emerge. If, and again, ding, 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 we only have one example, so we don't know what we're talking about, right? If life on Earth is like life everywhere, if it's a basic principle that life takes a long time to slowly evolve into blah, 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 people of some sort, and that's a big if. We think we think so, but on the other hand, we used to think our planetary system was the only model. So, okay, humility, right? We've got to not bother with the young, live fast, die young stars. They're unlikely candidates. We want to look at stars that are smaller, more like our sun, right? Yellow dwarfs, right? That was the first place we started looking. And that's the reason why all the science fiction authors, prior to like maybe 5 years ago or 10 years ago or so, the nearby to Earth, nearby yellow dwarfs, every science fiction author has an alien from Tau Ceti, and one from 61 Cygni, and Alpha Centauri, which is only 4 light years away anyway, is our closest neighbor, and it's perfect for our kind of life. We look for that. Now recently We've also started looking at red dwarfs. The color has to do with what the surface temperature is. Okay, and you know this from dealing with fires. The redder the light, the cooler the temperature. Okay, the red embers versus the blazing white, blue white, top of the flames. Anyway, so red dwarfs are cooler. They're older. There's been plenty of time, and that makes them a good candidate for looking for life. So that's another clue. Hey, what kind of star is it? What kind of orbit? Now, if you're looking for surface water, the planet needs to be closer in to a cooler star, right? It's like getting closer to if you got a little fire, you got to get closer, right? If it's a big blazing bonfire, then you have to step back, right? Same thing, the surface water zone will be farther out as the sun, the star gets hotter. All right, so you need a particular orbit. It needs to be a stable orbit, right? One of the first clues that Pluto was not a planet was when we realized that Pluto is not in the same plane, Plane, right? All the other planets revolve around the sun in the same, geometrical plane, right? And Pluto is going whoop, up and down and up and down. And sometimes it's closer to the sun than Neptune. So that was the first clue. It's got a really weird orbit. This is not a planet kind of orbit, even before we knew that it was, really tiny. So having an eccentric orbit like that, if it weren't a KBO, if it were running around like between the Earth and Mars, technically it's in the surface water zone. But if sometimes it's way, the average is there. If sometimes its orbit is like way up and all the way out towards Jupiter, and sometimes it's all the way in closer than Venus, then that planet, that life on that planet, has to be able to cope with 200 degrees below zero Fahrenheit, and boiling right at the other end. It's hard for life to adapt to that much, to be able to thrive in very cold and very hot, and okay, the more stable the orbit, the more stable the climate. Okay, so you also need to have enough mass. This is also physics. The planet needs to be big enough mass, that the interior, the core of the planet, remains hot and continues moving, and it's metallic. Because what do you know about moving metal, right? You're going to be generating a magnetic field. And that is what makes life on Earth possible, is that we have a magnetosphere, that it's like the Earth is like a big magnet, right? So we've got this protection. So when the solar wind comes blasting at us, it goes around, right? And of course, some of it, comes into the poles and creates all that beautiful aurora borealis and aurora australis. But it's not killing us. It's not stripping our atmosphere away, and the radiation is not killing us. Okay. That is what happened to Mars. Mars is too small. it wasn't big enough over the billions of years that the planets have been solidified. Its core froze, stopped moving, magnetosphere collapsed, protection gone, Mars's atmosphere was stripped away, the surface water was gone, froze, and whatever life, I'm going to say probably, arose there was doomed. Okay, doomed from the very beginning because there wasn't enough mass. Right, it's not something that you could terraform. If we decided to terraform Mars, give it an atmosphere, you know, and the surface water, so forth, right? Make an Earth-like planet out of it. We would have to be continually feeding the atmosphere because it's being blown away, right? Unless we've got a way to create a magnetosphere, at which point, wow. Anyway, so I've just explained about Mars. One of the things that all this new understanding has brought to us, all this new information, is like, why is NASA spending, you know, all this money? Why don't we spend money on Earth? Why do we have to give NASA millions of dollars to go explore the outer solar system? Because that's how we found out that Pluto isn't a planet, never was. That's how we've discovered that there's liquid water, warm liquid water out there in the outer solar system. And where there's liquid water, okay, now one thing, and I call this the curb your enthusiasm slide. Everything that a biologist can use to say, ooh, that could be life, that could be caused by life, can also be caused by chemistry. So, second bullet, you know, do a sampler, do an art project. Expect life only when you see multiple potential biosigns. Okay. One could be chemistry. Two could be chemistry. Three means send a probe, which is what NASA has done in sending multiple probes to Titan. In case you're wondering, why is Titan so exciting? 3 potential life forms, life signs. Okay. Right. Okay. From here, we're going to go to your next video.